Now welcome to this latest video on 162 Maths, and in this video we'll be going over the AS Math Statistics topic of probability functions and distributions. Now in statistics, a variable is classed as a collection of values. So for example, on the screen, if I was to ask students in my class what their favourite colour were, then X would represent their responses. So either be red, green, blue, orange, whatever colour that they choose. Then if each is assigned a probability of occurring, then it then becomes a random variable. Now, random variable X represents a single experiment or trial. It consists of outcomes with a probability for each particular value. Now, in terms of the notation, you'll tend to see this notation used a lot in this particular topic. Now, what this actually means, well, the P represents the probability that X represents the actual experiment. So in the above example, the capital letter of X, or the random variable X, is me asking students what their favorite color was, in which lowercase x would be their specific responses. So in other words, the outcome of an experiment. So if I was to roll, let's say, a dice, then the actual task of rolling the dice would be classed as capital X, and the outcome of me rolling the dice, so for example 1 2 3 4 5 6, would be the actual representation of lowercase x. Now in this, what we can find that in shorthand, probability of X equals X is written, but we can also write it as P of X. Now note that the lowercase of P. Now this is like saying the probability that outcome of my coin was thrown was heads. So rather than writing probability of heads, we'd write X equals heads versus the probability of lowercase p, in which the latter the coin was thrown was implicit, so we can skip the X equals. So now let's have a look at what a probability function is. Now, a probability function is a way of representing the values of X and a method of calculating their respective probabilities. Now, often this is written as numbers or as a function where the probability of an event happening is related to the numerical outcome. So this is an example of a probability function. So here we've got what the actual probability equals. So we're trying to find the probability of X equals X. Now, the values or the possible outcomes of X, so the possible outcomes of X is lowercase x. So in this particular example, the only values that we can have from this experiment are 1, 2, 3, and 4. Now, how we actually calculate the probabilities is by substituting X into this function part here. So these are the probability functions that connect X to its probability. So for example, here if I was to work out the probability of 1, then what I would do is I'd substitute 1 into this respective function. So here it would be 0.1 multiplied by 1, which is 0.1. To work out the probability of 2, I substitute X equals 2 into the function, so that's going to be 0.1 times 2, which is 0.2. To work out the probability of 3, it's going to be 0.1 times 3, which is 0.3. And to work out the probability of 4, I substitute X equals 4, in which I get the answer of 0.4. Now, for all other values, so for example, if I want to work out the probability of 6, then that is going to follow this function, in which it's going to equal 0. So for all non-values of X where it's 1, 2, 3, or 4, the probability is going to be 0. So, and again, X could be a negative number, in which it falls under this latter category, which gives me a probability of 0. Now let's have a look at a probability distribution. So in a probability distribution, this is where we represent X and their probabilities in the form of a table. So if we take the previous example, in which we've got our probability function here, so this is our probability function, then what we want to do is want to represent the values that X could be and their respective probabilities. So here I can have X values of 1, 2, 3, and 4, and here I have the heading of probability of X equals X, and what I'm actually going to do is write down the probabilities just purely in a table. So here, this is going to be where 0.1 times 1, so that's 0.1. This is going to be 0.2, this is going to be 0.3, and this is going to be 0.4. And again, how I've calculated those numbers is by substituting the x values into its probability function. And this table is what we call the probability distribution. So if you are ever asked to draw a probability distribution, then all it's asking you to do is to draw a table where you've got the possible values of x and their respective values of their probabilities. Now, before we get started working through some examples, it's really important that you make a note of these. Now, these are the key following points where they may not gain you marks, but they certainly do cost students marks if you fail to write these things down or acknowledge these. Now, one of the most important properties of a probability distribution is the fact that all of the probabilities in the table must add up to 1. So the sum must equal 1. And the reason for that is because the possible values of x, the events are going to be what we call exhaustive, so they all add up to 1. So whenever you are working with a probability distribution, particularly when you are asked to find the probabilities of each of these, and which this will make a lot more sense when we go through some examples, is to make sure that you always state that the sum of the probabilities, either written as p equals x or the probability of x equals 1. Now, another key property that you need to remember is that whenever you're writing a probability function, that you always include other values of x. So for example, if I had a function of x, and let me just change that notation because that is something else. So if I was to work out the probability of function, so let's say I've got p of x equals x, and you could use absolutely any letter at all. So let's say I had a sixth, and then I had, so that's going to be when x equals 1, 2, and 3. Then I could have a function where, and again, you don't always have to have a function, you could just have probabilities. So here then I've got a probability of, let's go for 2/5, and let's go for 3/5, in which x could equal 4 and this x equals 5. Now you might think to yourself, well, that's absolutely fine, but where students would lose marks is that they would then need to go on to write that the probability is 0 for all other values. And basically what that means is then when I'm doing my probability, calculating my probability, so I've got 1, 2, 3, 4, 5, and then I've got my probability of x equals x. If I was to convert this as a probability distribution, then this would be a 6th, this would be a 6th, this would be a 6th, and then these probabilities won't add up. So let me just change that to a 10, in which we've got 2/10 and we've got 3/10 there, in which then for any other values of x, so if x equals 17 minus 4, 10 million, that the probability would equal 0. So always make sure that you are, whenever you're writing a probability function, that you are including this notation here in your sort of diagram. So now let's have a look at our first example. So here it says the random variable x represents the number of heads when 3 coins are tossed. Now, if I was to write this in a sample space diagram, then it would look something like this. So this is where we are listing all the possible outcomes. And let me just amend the pen there. So this is where we are listing of all outcomes. So what we can then do is we can then refer this into a probability distribution. So x means the number of heads, so I can end up either with 0 heads, 1 heads, 2 heads, or 3 heads, and then underneath that I'm writing the probability of each of those events happening. I can then, from this, I could then go to and from a distribution function in which then I've got the probabilities of x. I've got where the probability is an eighth is when x equals 0 and 3, and when x equals 3/8, that is when x equals 1 and 2. And for all other values of x, which can't happen, the probability is going to be 0. Okay, so let's have a look at some example questions. So this question says the probability distribution is given as P of x equals kx for the values of where x equals 1, 2 and 3. And the question is asking us to find the value of where x equals 2. So to answer this particular question, what we need to do is just simply translate the probability function into a probability distribution. So here we've got the values of x, and x can equal 1, 2 or 3, and we've got P of x equals x underneath. And if I just complete the table, then to work out what the probability is, I replace the x value into the actual expression. So the probability of getting 1 is when x equals 1, so that's just going to equal 1k. Probability of getting 2 is going to be 2k, and the probability of getting 3 is going to be 3k. Now, as mentioned, one of the key properties of a probability distribution is that all of these probabilities need to add up to 1. So then we write as the sum of the probabilities is equal to 1, then what we know is 1k plus 2k plus 3k equals 1. So 6k equals 1, so k equals a sixth. So now that I know that a k equals a sixth, I can then rewrite, or redraw, I should say, the probability distribution, in which I replace the value of k. So probability of getting 1 is going to be 1/6, probability of 2 is going to be 2/6, and probability of getting 3 is going to be 3/6. Now I could simplify for the next two fractions, but I'm just going to leave it as it is, because with probability there's no insistence that you have to write fractions in its simplest form. Now looking back at the question, it says what's the probability of getting 2, so therefore the probability that x equals 2 is going to be equal to 2/6, which I can write as 1/3, and either of those answers would be absolutely fine. Now moving on to our second example, it says that a discrete random variable x has a probability function, and we've got our probability function here. And the question for A is show that k equals 1/6. So for this, again, we set up our probability distribution. So we've got x equals -1, 0, 1 and 2. And then we've got our probability function to work out the probability of each of those 4 values. So if I then substitute x equals 1 into my probability function here, then this value here is going to be k of 1 minus -1 squared. So minus -1 is positive 2, 2 squared is 4, so that's going to be 4k. Substituting x equals 0, so I've got k and then 1 minus 0 squared, and that's going to give me just 1k. Substituting 1, I get k and 1 minus 1 squared, which gives me 0, so that's going to equal 0. And substituting x equals 2, I get k, 1 minus 2, which is -1, squared gives me +1, so that's going to be 1k. And then as the sum of the probabilities needs to equal 1, then 4k plus 1k plus 0 plus 1k equals 1. Adding all of those up becomes 6k equals 1, so therefore k equals 1/6, which is what they wanted me to show. Now moving on to our third example, it says in a game at a fair, a ball is thrown at a rectangular target. The dimensions of the target in meters are shown in the diagram. The probability of hitting each region is proportional to its area. The price of hitting a region in the number is a number of chocolates equal to the number shown in the region. Find the probability distribution of the number of chocolates won. So for this, the question's asking us to draw a probability distribution for this particular game. So the first thing we need to do is we need to work out the areas of each section. So if I do that, in which all I've got to do is just multiply, so for this number 1, it's going to be 0.7 multiplied by 1, which is 0.7. Then I've got to do 1.2 times 1, which is 1.2. 0.7 times 1.2, if I do that on my calculator, I get an answer of 0.84. And 1.2 times 1.2 is 1.44. And then what I then need to do is work out the total area, which is going to be equal to 1.9 multiplied by 2.2, which gives me an answer of 4.18. So in terms of this, I could then draw my probability distribution. So here, the possible chocolates we could have are going to be 1, 2, 3, and 4. Now we could potentially have, so in a game a ball is thrown at a rectangular target, so we could have 0. So let me just add a 0 there, because you could miss the target completely, which is not something you want to do. In which, if I then write x equals, what I then need to do is then work out each of these probabilities. So the probability of getting a 1 is going to be 0.7 over 4.18. Probability of getting 2 is 1.2 over 4.18. Probability of getting 3 is 1.44 over 4.18. And probability of getting 4 is 0.84 divided by 4.18. Now from this, what you might think is, I don't really like writing decimals in a fraction, so we can then write these as whole numbers. So if I just type into my calculator, it should do the simplifying for me. So this gives me 35 over 209, then 1.2 over 4.18 gives me 60 over 209. 1.44 divided by 4.18 gives me 72 over 209, and 0.84 divided by 4.18 gives me 42 over 209. Now it's worth just double checking to make sure that all those numerators add up to 209, and let's have a look. It does. So the probability of getting 0 is actually getting 0 is actually 0. So I can write this like so. So you can write your probability distribution either what's written in red, or you can write it in what's written in purple. That should be fine. Personally speaking, I would go for the purple version, simply because we don't like writing decimals in fractions. Now moving on to our last example, the question's given us a probability distribution and it's asking us to find a potential range of values for x. So if I just start by labeling this as 1, 2 and part 3, then let's have a look at this. So to work out the probability that x is greater than 3, well, the values of x where it's greater than 3 is going to be 4 and 5. So that's going to be equal to the probability of 4 plus the probability of 5. So here, all I need to do is just add 0.2 plus 0.4, giving me a final answer of 0.6. Then for part 2, it's asking for the probability where x is between 2 and 4, inclusive of 2 but exclusive of 4. So the probability where x is within this range here is going to be the probability of 2 plus the probability of 3. So that's going to be 0.1 plus 0.3, which gives me an answer of 0.4. And then finally, for part 3, I need to solve this inequality. So I've got 2x plus 1 is greater or equal to 6. So 2x is greater or equal to 5. So x is greater or equal to 2.5. So what the question's asking me to do is to find that 2x plus 1 is greater or equals to 6 is equal to the probability where x is greater or equal to 2.5. Now the values of where x is 2.5 is going to be 3, 4 and 5. So here I just need to add the probability of 3 plus the probability of 4 plus the probability of 5, and working those out, I've got 0.3 plus 0.2 plus 0.4, which gives me an answer of 0.9. And there we go.